Okay, hi, so we're going to revise transformations of graphs. There are three types. We've got translations, stretches, and reflections in two different directions, parallel to the x-axis and parallel to the y-axis. That gives us 6 different transformations, and as a result, if we had a different rule to remember for each one, that could get really complicated. So I want to share things that will hopefully make it simpler. The first is the rule is basically always replace x or y with something. If we do that, we fix a whole load of problems with trying to remember transformations. It means there is complete consistency, particularly regarding the next one. The transformation basically always does the opposite, or rather, the replacement always does the opposite to what you'd expect. Okay, so if we subtract something, it goes in the positive direction instead of the negative. If we multiply, it gets smaller rather than bigger, and so on and so forth. The other reason we want to replace x or y with something rather than whatever method was taught at GCSE is because it makes it a lot easier when we're looking at complicated graphs. So, for example, if I give you Desmos, can I highly recommend using Desmos, by the way, and just play around with it. If you're getting stuck, type in the equation. It makes your life a lot easier to see what's going on. But if you look at this graph here, we've got the equation of a circle. It's not possible to just multiply the whole equation by something, which is what we kind of do, or subtract a number from the whole equation, because the equation isn't written in the form y equals something. So if I want to move it to the left, okay, I can replace y with y minus, sorry, 2 up, goodness me, I can replace y with something. And it basically gives a consistent approach whether the equation is written in a complicated way or a simple way. The other thing to do with Desmos is if you put letters in here, it gives you this add slider option. And that allows you to kind of see what happens as you add or subtract numbers. Okay, and it just allows you to play with things. So if I put a B in there, we can add this slider B and we can see what happens and see how it stretches or squashes depending on what the numbers are. Play around with Desmos, highly, highly recommended. Okay, but we're going to go through the algebra of it, since that's the questions that you'll be looking at, and we're going to go through a few different examples. So to start with, let's consider y equals x squared. Okay, we're going to translate this by 3, 0. Okay, and so graphically, that's going to look something a bit like this. Okay, mark on any points that you know, it will help you. If you don't know what it looks like, just guess. It doesn't matter if it's just a squiggle. Okay, just considering the picture will help you understand what's going on. So to translate something, we are going to translate this in parallel to the x-axis is our movement. So we're going to be replacing x with, and then the opposite. So instead of adding 3 to all our x values, we're going to be replacing x with x subtract 3. Okay, so we're replacing and we're doing the opposite. That simply means that y equals x squared becomes y equals x minus 3 all squared. Okay, if I wanted to translate by, say, 0, 2, this time we're going to be going up 2, then we're going to take our y equals x squared graph, and we're just going to be moving it up 2. Again, mark off the points that you know. Here, all of the y coordinates are being moved up 2. Okay, the x coordinate is staying the same. So we're going to be replacing y with, and again, the opposite, y minus 2 to move up instead of y plus 2. Here, y equals x squared becomes y minus 2 equals x squared. Now you may have written that at GCSE like this, y equals x squared plus 2, and that is very intuitive. All we've done is we've taken our equation, okay, or I should say, or I should say our normal y values, and we've just added 2 to the y value. That's very simple to understand, so don't forget that way of thinking about it. But if we think of everything as replacing y with something or replacing x with something, then we get a consistent approach across all of the transformations, and it works whether our functions are written as y equals f of x, or whether they are some function of x and y, okay, a bit like equations of circles or all sorts of other things. Okay, we can then start thinking about this transformation in exactly the same way. We don't have to suddenly change it. Okay, it works across the board. Okay. Let's just finish this off. This one up here, instead of y equals f of x, is now y equals f of x minus 3. That means wherever there was an x in the previous equation, we now have x minus 3 instead. Here, we've got y equals f of x. We're going to end up with y minus 2 equals f of x. Again, wherever there was a y in the equation, we now just have a y minus 2. Of course, if we wanted to move down instead, then instead of minus 2, we have plus 2. Plus 2. Plus 2. I think you get the idea. Okay, that's translations. Stretches. So now we're going to do a stretch by scale factor 3 parallel to the x-axis. Okay. First of all, sketch your graph. It's so important to helps you figure out what's going on. Okay, here's our sine curve, very roughly drawn. Stretch scale factor 3 parallel to the x-axis. So we're expecting this thing here to kind of stretch out in that direction there and there. Okay. So let's draw that. Let's just. So here we go. So this has got to be 3 times bigger. So we're going to get something that looks like this, and it's just going to continue all the way down there. And again, something that looks like that. It's going to be really quite large. It's the x coordinates that are stretching or moving. The height of these coordinates are staying the same. So it's the x coordinate that we have to replace. And here we want to multiply the x coordinate by 3, or that would be the intuitive thing. So we do the opposite. We're going to be dividing it by 3. We're going to have x divided by 3. So here, y equals sine x becomes y equals sine 3. Okay. More generally, any equation y equals some function of x becomes y equals some function of x over. Let's do the same, but this time we're going to stretch by a scale factor of half. So that's instead of a number greater than 1, we've got a number less than 1. This time, instead of parallel to the x-axis, we're going to be parallel to the y-axis. So again, let's start with our sine curve that looks a little bit like that. So stretch by scale factor of half in the parallel to the y direction. We're going to be looking at something that looks like this. It's going to be, we're expecting it to be sort of squashed. We'll call it a stretch still, or even an enlargement, oddly enough, even though it's getting smaller. So each of these y coordinates has been shrunk. Okay, so we would expect to divide them all by 2, scale factor of half, but we're going to do the opposite. So we're replacing the y's with 2y. Okay, If I wanted to stretch it by scale factor 2, it will be y divided by 2. If I wanted to stretch it by scale factor 1/2, it's 2y. By the way, that's the same as y over half. So it's consistent with the method above, just dividing by 1/2 is the same as times by 2. So the equation then becomes y equals sin x becomes 2y equals sin x. Okay? Or more generally, y equals f of x becomes 2y equals f of x. And again, you could rearrange this to give you y equals 1/2 f of x. Okay, acknowledging that each of these y coordinates is the original y coordinate has been divided by 2 to make it half the size. That makes sense. Don't forget that side of things. But again, the consistency of replacing y with 2y, everything is opposite and everything is a replacement of x, y in the direction of the coordinates. Reflections are the third and final one. Here we're going to sketch y equals x brackets x minus 2. That looks something a little bit like this. Okay, and to reflect in the x-axis, it's worth considering what happens to each point. So here's a point, it's going to reflect in the x-axis here, so we're going to end up down here. Notice it's the y coordinate that's changing, and so we would get something that looks like this. Okay, so here we're going to have to replace y with minus y. Okay, so consider what is happening to pick any coordinate, what's happening to the coordinates. The x coordinate is staying the same, the y coordinate is changing, and we replace it with minus y. So again, we've got this opposite idea going on. Over here, reflecting the y axis, we're going to get something that looks like this. Pick a single point. Okay, say this one over here. That becomes all the way over here. It's the x-axis, sorry, it's the x coordinate that's changing at that point. So we're going to replace x with minus x. And sorry, the equation would look like this. So we've got y equals x minus 2 becomes minus y equals x bracket. Over here, we're going to have y equals x bracket x minus 2 becomes y equals minus x minus 2. Okay, wherever there was an x, we replace it with minus x. We can then simplify that a little bit. I highly recommend taking your time with these questions, i.e. actually write down that. Don't miss that out. I find it helpful to avoid those silly, easy to make mistakes. I also find it helpful to kind of have a sheet where you've got all those rules written down. You don't need to copy this one, but this is the one that I've used in the past. And I just have it in front of me when I'm revising, when I'm working. And it means if I forget something, I can quickly remind myself. That looks a bit complicated. Write your own, it will help you. The other question that you might get asked is not to perform the transformation, but ask what transformation has occurred. So here, example, what transformation maps y equals x squared onto y equals x squared minus 4x plus 4. Seems a bit odd, okay? I highly recommend the following. Guess, test, repeat, okay? Often it's easy enough to look at these and think, oh yeah, I think it's one of those. And often you'll be right. But it's very easy to make mistakes. So I recommend, without fail, always double check. I'll show you what I mean. So here, we can go through some of these things and kind of try and figure out how on earth is that going to give us this. We've got a reflection. It's clearly not just introducing a minus to x or y. That's not affecting it. a stretch would be multiplying y by something that's not that, or multiplying x by something that's not that, or dividing by it. Again, that's not going to work. So it must be a translation. And so you can go through these logical steps that might help you to figure out what it is. And then guess. Now, here, let's say, I want to translate, let's guess the replacement first. So let's replace x. Now I've got to square it. I want to square it, I'm going to get a 4. So a 4 and a minus 4x. So let's replace x with x minus 2. Okay. And let's see what happens. So y equals x squared becomes y equals x minus 2 all squared, which in turn is given x squared minus x 4. So that's right. Here, this is our guess. This is our test. And now, and now we're going to just give our answer conclusion. Okay, because that was correct. So this is a translation by the vector to 0. Positive because we subtracted. And if that was wrong, I would just do another guess. And basically this is trial and error. Have a go at these two questions. Pause the video now. On the next slide, I'll give you the answers. And then here's my answers. Notice this time I have given an example where I've guessed, I've got it wrong, I've guessed again, I've got it wrong again, I've guessed again, and this time I'm right. And then here's my conclusion. I hope that's been helpful. Have a look at the questions in the textbook and on the booklet on transformations of graphs.